Okay, we are fact-finding in South Beach, but I'm never not thinking of my students back in Boston. So, courtesy of Ben Steinfeld, we have this problem number 23 from section 9.5, absolute convergence. So you have an alternating series, and the alternating series test, we want to take the limit of the a sub n, which is 1 plus n over n squared. If you forget, you divide top and bottom by n squared, and you'll quickly show that it goes to 0. Then, on the terms themselves, whether or not they're decreasing, then you make a little error, no problem, 1 point assessed. If the terms start at 2, then 3/4, 4/9, they're clearly decreasing. At this point, you can conclude that the alternating series converges. When we go to test for absolute convergence, we put absolute values around it, which essentially removes this -1 to the n plus 1. So now we're testing this series. Ben did it by the direct comparison test. He's a fan of that, along with Mark K. And you'd have to show that n plus 1 over n squared is greater than 1 over n. And this is 1 over n plus 1 over n squared, which is clearly greater than 1 over n. And therefore, because the series 1 over n diverges, this must as well. I use, instead, the limit comparison test because I find it very easy. So I'm going to compare it to 1 over n. I set up my limit. Do a little algebra. At this point, divide top and bottom by n squared, and the whole limit goes to 1. And since it's a finite limit, and since this diverges, then this series must diverge. So with absolute convergence, once you do the all positive terms, if that diverges and the alternating series converges, then you say you have conditional convergence. Just a word on the limit comparison test. Anytime you end up with the highest power and the numerator and the denominator are the same, it's going to go to a constant. That's why I often advocate using this test where you can. It's so easy. All right, I'm sorry to hear that it's about 8 degrees in Boston, and it's a little warmer down here.